600 into the vertical blank. Our highest scores have been ranked.
Atari ST STOS Basic Number 3. Speeding up sprite rendering. Intro. When you look at the Gorf arcade game here, especially level 1, Invaders, you see a number of enemies in formation. In fact, there are 27 aliens lined up in 3 rows of 9 each. STOS has a built-in limit of 15 sprites. If we were to create a game similar to this, using one standard STOS sprite for each invader, we'd use up our entire allotment of sprites before we even got to the 3rd row, and not have any left for the player or missiles. There are multiple ways to achieve the effect of having a group of 27 sprites march across and down the screen in STOS. We'll look at 6 of them in this session. If we try to use individual 16:8 images for each of the invaders instead of STOS sprites and copy them directly to the physical screen, we would be limited to moving them in 16 pixel jumps left and right. This obviously will not look very clean and certainly not like the arcade game. This is the problem that STOS sprites were intended to solve, but we don't have enough of them to have each of the 27 16:10 invaders occupying an individual sprite object. We could attempt to do something like using 9 sprites only for the invaders, where each sprite represents a column of 3 invaders. This could actually work, as it would leave us with 6 more sprites for the rest of our game objects. The problem here is that with the player ship, missiles, Gorf mothership sprite, and other needed graphics, we are nearing the 15 sprite limit, and rendering will be much slower than we want. We'll try this though and see how it works. We could try various types of pre-rolling and pre-shifting the sprites or formation for quicker throughput that is faster but uses more memory. We could also use one of the STOS extensions like Misty or MissingLink to do the pre-shifting. Today we are going to test many of these methods, look at the results, and pick one for our game. The invader formation at level 1 is where we're going to concentrate the bulk of this tutorial. Again, we have 27 invaders and we want to move and animate them across the screen as a group. Each invader has 2 frames, represented here. I created these using the Champ Games Gorf Arcade for the 2600 as a guide. I zoomed into images from it in a Windows graphics program, and using Neochrome on the ST, I was able to duplicate them by hand. Neochrome is a very nice tool for hand drawing Atari ST graphics because of the way it zooms in and separates pixels. This was the easiest way I could find to get clean color graphics for the arcade sprites for this demo. We are not going to use these graphics in our game. This is just for a demonstration. Gorf by Bally Midway used copies of the Space Invaders sprites. They seemingly had the rights to do this because they distributed Space Invaders in the USA, or at least they thought they did. Again, we're not going to copy any graphics or sprites from an arcade game. We're going to use our own, but for this demo, I wanted to have something clean for us to look at. Here is our sprite sheet so far. It's saved as an uncompressed Degas file called grSprpi1. We will not be loading this directly into our game, but instead we're going to use the STOS Sprite utility and the MissingLink extension to create memory banks of sprites for us to use. Invader 1 Frame 1 and Invader 1 Frame 2. Here's Invader 2 Frame 1 and Invader 2 Frame 2. Here's Invader 3 Frames 1 and 2. And here's an entire column that I created of sprites. We're going to be making use of this one today. Our goal will be to create a formation of invaders that move across the game screen using the best frame rate possible on a standard 8 MHz Atari ST. Remember a couple things before we start. First, there are usually more than one way to solve a game development problem, and I'm not saying that my way is the best. Also, we will use any part of standard STOS or an extension that we feel will give us the best gameplay. I've saved all these sprites in a memory bank called grspr.mbk. We've also created a MissingLink Bob file called bobspr.mbk. We will explain how to use this file in our final test, number 6 for the day. While we're giving you all of the code, and in the first 2 tutorials we demonstrated how to use VS Code, there's no need to follow along exactly in VS Code to get something out of this tutorial. You can though. It will help a lot to be able to load in the files and take a look at them, as we'll build off of them as we continue to make Grief. All of the code can be found in our new GitHub project here for Make a Thing. There's a folder here called Grief. Let's quickly show how to make a new VS Code project if you have the stoscoders.com VS Code plugin installed. First, we make a new project for Grief in VS Code. Press Ctrl or Command plus Shift plus P to open the command palette. Type STOS, choose STOS New option, put in the address where you want to create your project. The project name I'm using is Grief, but you can call it anything you like. I've also copied the Grief spr.mbk to the Grief STOS folder. We're going to continue with the concepts we started in Basic STOS number 1 and 2, and also from the tutorial I did a couple years back on using bobs in MissingLink. The first thing we're going to do is create a simple frame rate counter so we can compare the throughput of these various rendering methods. Frame rate counter. The goal of the frame rate counter is to measure how fast each of the 6 rendering methods works for our game. We will need to make use of wait VBL, some counters, and a little basic math to enable us to accurately measure the frame rate. Before we start a render loop, we must do this. We must first set the timer equals 0. This command sets the internal STOS timer to 0. It increases by 1 every 50th of a second. 2. FCTR equals 0. This is not a STOS command, but a variable we have created to count the number of frames that have occurred total in our render session. 3. FPS equals 0. Also, not a STOS command. This is a variable that will hold the current calculated frame rate of our test. 4. SE equals 0, another custom variable that will keep count of the total number of seconds elapsed during our test. To implement this, inside our render loop, we will either render graphics manually, or in case of the first test, STOS Sprites, we will render with the built-in commands on their own interrupt, and we'll just use the wait VBL to count the frames left for our code other than the sprites. We're going to inc the FCTR, that's increase the frame counter. This adds 1 to the current value of the frame counter variable. Next, we check if the timer is greater than 50. If it is, we increase our seconds elapsed SE by 1 and we set the timer back to 0 so we can count up to 50 again. The timer counts based on the frame rate, so we know that when it hits 50, 1 second has elapsed. We'll increase the SE variable by 1 and then set the timer back to 0 to start over again. 1 second elapsed for every 50 timer ticks. This is a biggie. Once we have 5 seconds elapsed, SE equals 5, then we know there should be enough frames counted in the FCTR, or frame counter, to not get a divide by 0 error. We then calculate the current FPS by dividing the number of frames counted, FCTR, by the number of seconds elapsed, SE, and print it on the screen. We'll see this in action in the 6 render tests that will start now. Render test 1, using 9 STOS sprites. Here's what we're going to do. We're going to put 9 sprites on the screen, each using the image 7 from the grspr.mbk. This is the column of 3. The size of this is 16 pixels by 30 pixels, 16 pixels across by 30 pixels high. We'll put them on the screen in a loop like this. Here we are simply adding 1 Sprite 7 to the screen every 16 pixels, starting at 0, 0. We will then move the sprites in a loop with the move command. They will start moving with the move on command. This is not new. We did this with a single sprite in the first tutorial. Next, we'll have our FPS counter code. Since STOS sprites run in their own interrupt and not in the vertical blank, we have to make sure we use wait VBL to accurately count the number of frames left in each second for game logic, other graphics, etc. We do this in a repeat until loop until it counts to 200 frames and then stops. Now let's run the precompiled rend tst1.tos and see the results. What you will see is the formation crawl slowly across the screen and finally output 2 frames per second as the result. This is not good. While this basic FPS counter is not going to be 100% accurate, it's a good enough estimate, and the eyeball test tells me this is not fast enough for our game. Render test 2, using the vertical blank to update STOS sprites. In this test, we're going to use the 9 STOS sprites again for our formation, but we're going to turn sprite automatic updates off and we'll update them in the vertical blank along with our FPS timer. Much of the code is the same as before, but here's the key difference. Move off stops any current sprites from moving. This is here just in case there were sprites moving before this part of the game. There are none, but this is a clean way to make sure to stop all sprites from moving before you start. Update off will stop sprite updates from showing on the screen until you issue the manual update command. We'll do this in our repeat until loop. Here is that loop. The FPS counter has not changed. The only thing we've added is the update before the wait VBL. Okay, that's it for this one. Let's take a look at the results of render test2.tos. Okay, this helped a little bit. The sprite still crawls slowly across the screen, but we get 7 more frames a second, and a little bit smoother of a render. There are still some skipped pixels and little jumps, but it's altogether a little bit faster. We have a ways to go before we have enough speed for a real game though, so let's move on to the next test. Render test 3, moving STOS sprites manually. In this test, we will still use 9 STOS sprites, but we will remove the move command altogether and set a dx or delta or change in x value to 1 pixel on each frame on the x-axis. The code for this test is very similar to test 2, but we are removing the loop that sets up the move commands and adding 2 new variables defined outside of our render loop. The first one, dx equals 1. This is the change in x on each frame, basically a constant rate of speed of 1 pixel. 2, sprx equals 0. This holds the x position of the leftmost sprite, sprite 1. This is used to calculate the x position for all 9 sprites on each frame and is also used to calculate when the formation needs to stop and move in the opposite direction. Inside the render loop, we have some changes. This code is used to loop through all 9 sprites and update their respective x positions 16 pixels apart. On each render frame, we increase sprx by the dx value and check to see if it's greater than 172, meaning the rightmost sprite is at the right edge of the screen. If so, we change our dx to -1, so the formation will march in the opposite direction. We also check to see if sprx equals 0, meaning the leftmost sprite has hit the left edge. If so, we move them in the opposite direction. Let's take a look at how this performs. This looks about exactly the same as render test 2. It's time to move away from STOS sprites to see if we can figure out a way to really amp up the frame rate. Render test 4, offset pre-roll scrolling. In this test, we'll use screen copy to create the illusion of the formation moving smoothly across the screen in 1 or 2 pixel increments. This is the one I've been thinking about for a while now, but just in the last few weeks I found time to test. When I was playing with the blitter commands, I discovered, well, I have no idea if I discovered it or not, but I've not seen it anywhere else. I'm sure it's a pretty standard way of doing things for the seasoned ST or Amiga programmer. I just have never come across it in my limited perusal of the topic. So this is what we're going to do. We're still going to use the 9 sprites, but only as a way to set up the initial formation. We will then copy that to a screen memory bank, screen 10, and place it at an offset of 16 pixels. Screen 10 will look like this. The yellow line won't be there, and the 0 and 16 won't be there. That's just for demonstration. But what it will look like is all of the sprites in the formation will be offset 16 pixels from the left. The invaders are drawn starting at 16px and 0y. Because screen copy allows the source of the copy to start at non-zero and non-multiple 16 increments, we can use this offset as if we were scrolling the invaders across a set of 16px wide tiles. We have to do this because the destination of the screen copy must be 0 or a multiple of 16. I know it sounds a little obtuse now, but it will become much more clear. For example, if we want to place the invaders at position 157 on the physical screen, we would need these 3 pieces of information. 1. We would need the X position we want the invaders to look like they're at on the physical screen. We have it. It's 157. This is the variable x1 in our code example. The offset back from the first invader inside those first 16 black pixels to the left of the invaders is stored in a variable called xoff. This is the x offset back. And we also need to know the total length to copy from. The offset is pretty easy. If we divide 157 by 16, the remainder is the offset. We do this with the mod math function. 16 goes into 157 9 times, and the remainder is 13. Our xoff equals x1 mod 16, or xoff equals 13. The screen copy function we use would look like this. Let's break it down. 1. Screen copy. This is the built-in STOS command. 10. This is the source screen or memory bank for the copy from. 16 minus off. This is the X location to start the copy, or in this case 16 minus 13, or 3. We would start our copy from the 3rd pixel. This is the Y location to start our copy. It's 0. This is the X2 location, or the end of the rectangle to copy from. xoff plus 160 is 13 plus 160, or 173. The Y2 location, this is 30. The formation height is 30. Then the word 2. This is part of the STOS command to let STOS know the location is coming up next. Logic, this is the screen to place the pixels on from screen 10. X is the location destination for our copy. This will be stored in X1. This will be 157. And finally, the Y location for our copy is 0. We want to place the formation at 157, 0. The actual X location to start our copy from on screen 10 is 3. This will allow it to look like the first pixel of the left column of aliens is at 157. This is an offset scroll and is very effective for quickly placing objects at any X position you need them to be on the ST's physical screen. After we do the screen copy, we want to update x1 by dx and then check to see if we're at the far left or far right and turn the formation back in the opposite direction. Let's take a look at this in action. Wow, what a difference. We're hovering around 28, 29, 27, and 30 frames a second. This moves very smoothly. This could be a candidate for how we'll do our moving game objects. Let's try a couple more ideas and see if we can squeeze a little bit more power out of STOS on a plain old ST. Render test 5. Create our own pre-shift image array. Render test 5 takes a new tack and starts us down the path of storing what are called pre-shifted versions of our sprite in memory and then blasting them to the screen when needed. If this sounds familiar, it's because many ST programmers talked about using this tactic to make playable and fast 16-bit games for the ST back in the 80s and 90s, and extensions for STOS such as MissingLink perfected it for making games in BASIC. We're going to test MissingLink next, but first, to get an idea of what is involved and to see if we can do this ourselves, we're going to test our own pre-shifted sprite. We are going to take one column of 3 invaders and store versions of it in each of 16 possible positions. To display the formation, we'll need to use a mod command very similar to what was used in the previous render test 4's pre-rolled scrolling formation. We will need to create a pre-shifted array of screen strings using the screen string command to create and store these images in an array. The FM $16 will hold all 16 pre-shifted images of the sprite. Inside this loop, we will draw a sprite to the screen, like this. Sprite 1, x, 0, 7. We will then replace that sprite with a rubber stamp of the sprite on physic with the put sprite command. We will wait until the vertical blank, turn the sprite off, but the rubber stamp put version will remain on the screen. We will then use screen as a string and copy the 32 by 32 chunk of the screen to the array at the current array index x using the screen string command. We will then repeat this operation, increasing x by 1 for all 16 positions. To display the formation, we need to show 9 copies of it on the screen, much like render tests 1, 2, and 3, but using the screen string graphics and not STOS sprites. We set up our CTR loop to start at 0 and move through all of the array elements in the FM string array. The x value to start drawing any of the 9 sprites is x1 plus CTR times 16. The offset, or the actual pre-shifted sprite to display at that position, is calculated pretty much the same as with the offset formation we did in render test 4. X off equals x mod 16. We then place the image from the array at the correct x and y position and move to the next column. I predict this will be much faster than using 9 STOS sprites, but not quite as fast as a single offset pre-roll scroll used in render test 4. This is because we have to do 9 separate, smaller draw operations, one for each of the 9 columns, as opposed to one single draw operation on the pre-rolled formation. For size comparison, we have 9 times 32 times 32 is 9,216 pixels. That's for this version. And we had 5,600 pixels, which is 176 times 32, that was used in render test 4. Let's take a look at the results. Wow! 28, 29, maybe even 30 FPS, not bad at all. The extra memory used to store the pre-shifted array almost completely made up for the double amount of pixels that need to be displayed on the screen. I do think I could do one further test using plain old STOS, which would be to pre-shift the entire formation, not just a single column, and put those in an array. That would use up a lot more memory, but mean only shifting 5600 max pixels from the array on any frame. But instead of doing that, let's take a big step. We have proven that plain old STOS is fast enough to make a pretty decent version of what we want to show, but I want it even faster, and that means using the MissingLink extension. Render Test 6, MissingLink. I have a previous video and tutorial that shows the basics of MissingLink. I'll link to that below and in the blog post that goes along with this tutorial. I don't want to spend a lot of time repeating what I've done before, so please take a look at that for more information if needed. I created a set of Bob sprites using the MissingLink make utility. You will find bob.spr.mbk in the GitHub and also the full set of MissingLink documentation, demos, utilities, and tools. In future tutorials, while we finish this game, we will explore MissingLink in copious detail. For now though, I'll summarize what it is doing and how we will achieve as much speed as possible in STOS using this incredible extension. Much like Render Test 5, we'll be using 9 columns of pre-shifted data to display the invader formation. We need to set up a series of arrays to hold data for the bobs we're going to use in place of sprites on the screen. MissingLink loves arrays of organized data, and so do I. Because there are no complex data structures in STOS and multi-dimensional arrays are very slow, we're using a concept called parallel arrays to hold all of our data. Don't let the name confuse you. It's just a bunch of lists of data all organized by the same array index for each bob we want to display and manipulate. We're going to have the XBob array, the YBob array, the SBob array, and the iBob array. These are standard MissingLink arrays that are needed for the many-bob command. This will hold the X position, the Y position, the status, and the image to display currently for each bob. I've also created 3 of my own arrays, DXBob, DYBob, which hold the X and Y change in position, and ABob, which is to animate it or not. Animation is not going to happen in this tutorial, but we'll need it when we go further. The following code loops through all of the arrays and sets the initial values for the bobs. Here, next, we create memory pointers to arrays. MissingLink makes heavy use of C-style coding that interfaces directly with machine language to greatly speed up operations. That being said, the var pointer is a standard part of STOS, not part of MissingLink. Including this var pointer was a great thing for the STOS team to put in. On each frame, we're going to do this. First, we're going to call the MissingLink wipe command, which is a very fast replacement for the STOS CLS command, almost twice as fast. Then we're going to call the many-bob command. This will blast our 9 bob sprites to the screen to make the formation. Then we'll call the many-add command, which is a super fast replacement for a loop through an array. We're going to use it to add the DX value to the X position on every frame for all 9. And that's it. The final if statements use the XBob 0 value to determine the DX for moving the formation left and right. That's all we have to do. Also, if you haven't done so already, make sure you add the extension files to both the STOS folder and the compiler folder. Now, how does it perform? +50 frames per second? Now that's fast. It's just an estimate in an emulator, but it shows that using this method, the ST and STOS are barely breaking a sweat with the 27 sprite formation. And this is why we'll be incorporating MissingLink as much as we can going forward to make our game and continue along with grief. Next time, in the next session, we'll add the player, missiles, and collision detection. Until next time, into the STOS and Atari ST vertical blank, literally using the vertical blank.
Programmed in BASIC, we explored 8-bit
An 8-Bit Rocket Studios production.